Hello, good evening. My screen is visible. Yeah, thank you. I'll wait 2 minutes more. Let's other join. Okay, then we'll start today's session. Good evening to all. So today is our third session, and we'll do some problems on Mohr circle and on three-dimensional representation of stress tensor, and some problems we will solve for principal stress and octahedral stress, octahedral shear stress, octahedral normal stress. So before that, I'll just I saw that some people had doubt regarding the like when we draw some bending moment diagram or shear force diagram. So the representation of reactions is an important thing. So what happens actually that we need to consider that whatever is maybe the case of simply supported beam or cantilever beam. So first of all, as I had told last time also, we need to do what to find the support reactions. So actually what we are doing, we are idealizing it. Okay, so in the model, it's an actually model. So what we do, we actually idealize. So same support can be idealized in a different manners. So that's very important. So first what I had told last time, that we have to make a section which is very close to the support. Okay, so we have to cut at the beam at those sections which is very close to the support. So if we do that, suppose I am talking about the simply supported beam. So if we do that, so what will be the result? Something like this. So we will have a vertical reaction at this point A, and a horizontal reaction at this point A essentially, and we will have a vertical reaction at this point B. Okay, now so this is why I am emphasizing here, because we have to like everyone should be clear that what support gives what all as constraints. Okay, so it's very important that this is a hinge support and this is a roller support. So a roller support gives only a reaction in vertical direction in this fashion, whereas the hinge support gives two reaction components, one vertical, so it arrests the vertical displacement as well as the horizontal displacement basically, and accordingly it gives us the reaction there. But yeah, so further if I say that there is no load in x direction, in this case if I say only vertical loads are acting, there is no load in x direction, so obviously the horizontal component comes out to be 0, and we can remove this component and we can live happily with these two components. Okay, so similarly if we look for the propped cantilever beam, so again what we have to do, we have to cut the beam at the near the supports. Okay, very near to the supports. So what will happen if I cut? So as you know, this is a fixed end, so we'll have a vertical component of reaction at A, we'll have a horizontal component of reaction, and we'll have a moment also, moment at A. And similarly this is a roller, so we'll have only a vertical component of A. Okay, so now again why we are doing this exercise, because we should know that which support provides how many constraints. So to ensure that and to like learn it in a proper way, I am doing it, because when we go for SFD, BMD, there it is very important to understand this. So again if I say that there is no horizontal force in the beam, only vertical force is acting, so we can make this component as 0. Okay, so we can happily live with MA, that is a movement, VA, this will be VB here, won't be VA, it will be VB, vertical component at B. Okay, similarly we can draw for cantilever beam, again same principle, we have to cut near the support, there is no support at this end, so the final result will be something something like this. So we'll have a vertical component at A, we'll have a horizontal component at A, and again a movement, okay, and A. Okay, we'll have a movement. So because this end is a free end, so there is no constraint due to the support. So again same principle, if there is no horizontal force acting, we can say that this component is we can just remove this component, so we'll have only MA and VA. And finally for fixed beam, so again same principle, cut it very near to the support, and then put the all the reactions which we will get. So we will get vertical at A, we will get horizontal at A, we will get a moment at A, horizontal at A. Similarly we will get vertical component at B, we will get horizontal component at B, and we will get moment at B. Okay, so again using the same principle we have to see, but in this case is a case of indeterminate beam, so like that we need more number of equations, because we have more number of unknowns here, and the number of equations are less, so we need more number of equations to solve this problem in this case. Okay, so this was just a brief thing, like how to represent properly the supports. Okay, so that we should know the meaning of each support, what all it can offer as in constraint. Okay, now moving to the this week's class, so this week's session. So as you might have gone through the week 3 lectures for the strength of material course, so here in the last week, third week lecture, we had seen that we have seen the Mohr circle and the proof of Mohr circle, why Mohr circle will always be a circle. It will always be a circle. So professor has proved that mathematically there. And then we have seen principal stresses. So how to compute principal stresses for the case of 2D as well as 3D, a general case of 3D. And then we have seen the subsequently the components of stresses on some specific planes like octahedral plane, something called octahedral plane. So we had octahedral normal stress and octahedral shear stress. So we'll solve some problems regarding that, so that it will be helpful for you to solve assignment questions. So that will be what we will be doing in today's class. So I have one more request, that from now onwards, for subsequent sessions, I'll request you to have your scientific calculator with you, because it will be very helpful. Because once you do it yourself while solving, because there is an ample amount of time here, 2 hours, so we can solve it very at a medium pace. So you can solve with me, so that you will be more confident in solving the assignment problems. So I would suggest that if you, those who are solving problems in the session itself, so have a scientific calculator with yourself, and it will also help me to, because when I will be writing answers, so I'll take help from you to, so that you can solve it in calculator, and just we can put the values there. Okay, so let's see about the first question. So I have taken, last time also we discussed the Mohr circle for a very basic problem, very simple problem of pure shear. So this time I brought a little bit different problem, a mixed kind of problem, where you have a fully populated stress tensor, and it's a plane problem. Okay, so here the question states that the state of stress of plane stress at a point is shown in figure. So you can see the state of stress. Find the center and the radius of Mohr circle for the given state of stress. Finally draw the Mohr circle. Okay, so we'll first find the radius as well as the center of the Mohr circle, and then we'll draw the Mohr circle. And what I'll do, I'll also write the equation of the Mohr circle, the equation of the circle, so that after the session you guys can use any plotting software, like even in MS Excel you can plot that, and you will see that what we will draw the circle here, exact circle you will get there from that equation. So that I'll do, so that you guys get accustomed with the equation, because that Mohr circle equation is very important. So, and it comes from the stress transformation law. Basically, when we transform the stress from one coordinate basis to another coordinate basis, suppose x comma y to x prime comma y prime, so from that we get the Mohr circle equation, and that has been properly solved and explained in the lecture itself. So you can go back to the lecture and see it. So we'll solve this first problem. So we have, as you can see that, so what we have, that we have a sigma xx value, we have sigma yy, and we have tau xy. But you have to be very vigilant about the directions which I have shown, the arrows. So you have to be very careful with that, because that will be incorporated in the stress tensor matrix. So how that stress tensor component sign changes, that is very important. So let's solve first problem. Okay, so in the first problem, we have, this is y, this is x, we have a on next plane we have 25 MPa as our stress, acting stress in X plane. In Y plane we have 50 MPa. And you just look at the directions of arrow, 50 MPa. Okay, and then we have shear also, something like this, So the magnitude is 10 MPa, and equality of cross shear makes this also 10 MPa. Okay, so first of all we will write the stress tensor from this. So we'll write the stress tensor matrix. Let's do that. Stress tensor sigma. So I would suggest you guys also write yourself. So you can see that this direction is my positive x and this is my positive y. Okay, so now we knew that sigma xx, what it means, the first one shows the plane and the second one shows the direction. Okay, so you can see that the 25 MP which I am showing here is in inward direction, opposite to positive x. That's why it will be minus. So this will be minus 25. Okay, similarly sigma yy we see, so it is acting in the direction of y itself, so it will be positive. So it will be positive. And again just check the sign of shear, that is tau xy. So tau xy is in x plane and in positive y direction, but you can see the arrow here is in downward, which is negative y direction. That means it will be minus 10, minus 10. So this will be the stress tensor. So from there we can easily identify that sigma xx is minus 25 MPa, sigma yy is 50 MPa, and tau xy is minus 10 MPa. Okay, now what is the equation of, because we need to find the center as well as the radius of the Mohr circle. So let's first write the equation of Mohr circle. I'll write a generic equation. So we'll write equation of Mohr's circle. Okay, so I'll write a generic equation. So generic equation is like x prime y prime sigma x prime y prime, not y prime, sorry, sigma x prime minus sigma xx plus sigma yy by 2, this as whole square, plus tau x prime y prime whole square is equals to capital R square, where capital R is, or capital R square is sigma xx minus sigma yy by 2 whole square plus tau xy whole square. Okay, where sigma x prime y prime and tau x prime y prime is the stress component sum in any coordinate, any direction. Okay, it could be any plane. Okay, so this, so from there you can see that the center of Mohr circle is what, sigma xx plus sigma yy whole divided by 2 comma 0. You can see that because with tau there is no term, but with sigma term there is a term is there. So this will be the center. So now we know the value of sigma xx and sigma yy, so we can just substitute there to find the answer. So the center will be minus 25 plus 50 divided by 2 comma 0. That will be 12.5 comma 0. Okay, 25 divided by 2, that will be 20.5 comma 0. Okay, now the radius. So again you know the expression for radius. So radius expression will be the square root of this term. Actually this is r square, so r will be square root of this value. So let's find first this value. So again we have the formula, that is sigma xx, that is sigma xx is minus 25 minus 50 whole square, first I'll put divided by, so divided by 2 whole square plus tau xy square. So tau xy is what for us? Minus 10. So minus 10 square. So this will be 37.5 minus whole square plus minus 10 whole square. So if I find this, the square root of this I'll put here, okay, square root of this. So if I find, the radius comes out to be 38.8104, and I request you all also to try with yourself. You also try to find this value. It will be in MP. Okay, so it will be around 38.8104 MPa. So we found the radius as well as the center of the Mohr circle. Okay, now the question says that we found that center and radius. Now it's asked to draw the Mohr circle. So we'll try to draw it, because last time we took a simple problem. This time it's a little bit involved. So like we have few more components. So we'll try to draw the Mohr circle. So drawing Mohr circle. Okay. So first I will represent the x and y axis. So this is vertical, horizontal. So this is sigma, this is tau. Okay, and this is the origin. Now first we need to locate what? We need to locate the x plane and y plane. Okay, so I'll write the situation. What is the situation in x plane and y plane? So right, stress tensor components on x plane. So x plane, which all you have sigma xx, which is what? Minus 25 MPa, and tau xy, which is minus 10 MPa. Okay, so as you remember that, and okay, I'll write stress tensor components on y plane also, then I'll explain. So here sigma yy is what? 50 MPa, and tau xy is what? Minus 10 MPa. Okay, so as is been explained in the class also, what happens when you draw the Mohr circle, you have to be aware of what the shear is there. Okay, so the positive shear, while drawing the Mohr circle, the positive shear is drawn downwards in the negative direction. But you here in this question you have a negative shear, it's not positive. That means something, we have to do the reverse of it. So if the positive shear is plotted downwards, the negative shear should be plotted upwards. Okay, and that's why I chose this question. Okay, so that you should be you should be aware, remember that property. Okay, and we only look at the shear on the xy plane, for only xy plane, not anywhere else in y plane. Only the shear on the xy plane, the positive shear on the xy plane is plotted in the negative direction, but we have already negative shear, so we'll plot it in positive direction. Okay, so but the sigma xx component remains same. So obviously from this you can see that sigma xx will be plotted in this region. Okay, and our tau xy will be plotted in positive region, that means in this region. So somewhere our point will lie here. So we'll say suppose this as the x plane. Okay, and what is the state of stress here? It is minus 25 comma 10. Okay, now we have located the x plane. Now coming to y plane. So y plane we have uh, sigma yy as 50. That means you have to plot it in positive direction, in this direction, and the sigma x tau xy is -10, and that will be done in a conventional manner, that is in the negative direction, so that it is downward. So this point will be somewhere lying somewhere here. Okay, so now that from this if we just join these 2 points, we'll get the if we join these 2 points something like this. So now we need to just draw a circle. Draw a circle which passes through these 2 points. Yeah, like that, something like this. So it should pass through these 2 points. Okay. Yeah. Considering that as a diameter. So this becomes our this point where it intersects becomes the center. This becomes the center, and which is we know already what is the center. So we have found the center will be 12.5, 0. So this will be 12.5, 0. It is actually lying there, so I have to just move this little bit here. Okay, so this is 12.5, 0, and we have drawn the circle. We have drawn the Mohr circle. Okay, so from this, if you want to find for any plane, basically you can find the values of the principal stresses, which you can find, which will be what, if you have done the lectures, you will be remembering that this is 1 principal sigma 1, this is sigma 2. I'll represent it with, this is 2. So from here we can find the principal stresses also. Okay, and there is also a direct formula, so I'll do what I will find the principal stress also. So we have principal stresses. Okay, so we have formula for principal stresses, sigma 1, sigma 2. So sigma 1 is sigma xx plus sigma yy divided by 2 plus square root of sigma xx minus sigma yy by 2 whole square plus tau xy square, that is sigma 1. So if you see, this expression is nothing but the radius basically, and this is the center coordinate basically. So we know these 2 values. So what we can do, we can directly substitute. So sigma 1 plus sigma xx plus sigma yy by 2 is what? It is 12.5, and we have found the value of radius, so it will come out to be 38.8104. Okay, so if we just add these 2 quantities, 38.8104, so we will get 51.3104 MPa. Okay, that will be sigma 1, and sigma 2 will be sigma xx plus sigma yy by 2 minus square root of sigma xx minus sigma yy by 2 whole square plus tau xy square. Okay, so for the case here we have plane stress, so it is easier to use these formulas to find the principal stresses. For 3D case, because the next problem which we will solve today, it is a 3-dimensional case, so we'll try to see how, if a 3D case comes, so how we can solve for the principal stresses. Okay, so it will be 12.5 minus 38.8104. So 12.5 minus 38.8104. So it will come around minus 26.3104 MP. Okay. So as you can see that sigma 1 is coming positive and sigma 2 is coming negative. So you can see also that our sigma 2 is in negative x direction or x sigma direction, and sigma 1 is in positive direction. Okay. So basically it's a check also. So mathematically we are trying to find from the equation, but when we are looking at the Mohr circle, you can see that it is falling like that. So what I will suggest you, like how to verify your results, what I will suggest you, you just draw the draw the equation of this circle. This, you already know this component and you know R. So what you can do, you can use any software to just plot this. So you can replace sigma xx for the time being with x, and sigma yy for the time being with y, tau x prime y prime with y. So it is like x minus 12.5 whole square plus y square is equals to r, that is 38.8104 whole square, and you try to plot it. So once you plot it, you find this point in there and this point in there. You will see that this point will match with the result which you are getting from the equation, and the other point also, if you see, you will see the result will be matched with this. Okay. Now if we can even find here the maximum shear stress, because we got the principal values. Okay, so we can even find maximum shear stress. So maximum shear stress. So maximum shear stress, that is called tau max, is equals to sigma 1 minus sigma 2 divided by 2. For this is I am writing for plane state of stress, and condition that sigma 1 is greater than sigma 2. Okay, so I have written sigma 1 and sigma 2 in that fashion only. Sigma 1 is greater than sigma 2. So that's how we found tau max. So tau max will be, value will be what is sigma 1? 51.3104. 51.3104 minus of 26.3104 divided by 2. So the minus will get cancelled with the other minus. It will be 51.3104 plus 26.3104, that will be divided by 2. So it will come out as 38.8104 MP. Okay, and essentially that will be the radius of the Mohr circle. So if you plot in some software, what I will say to look to you, so that you look at this vertical line which is passing through the center of the, what you do, you draw a vertical line. I'll represent in some other color, green. So draw a vertical line passing through the center of the circle. Okay, and you find the ordinate of this point. Basically this quantity will be tau max, this quantity will be tau max. Okay, so this is that, and even you can find the principal planes also here. If you want to find principal plane also, you can do that. So what we know about principal plane, we have all principal planes. So we have seen that how we find that. You know that tan 2 theta is 2 tau xy upon sigma xx minus sigma yy. Okay, that is the equation we know. So tangent of 2 theta will be 2 times tau xy. So what is tau xy for us? Minus 10, and sigma xx is minus 25 minus sigma yy is 50. That means minus 20 divided by minus 75. Yeah, so our theta will be half of tan inverse of minus 20 by minus 75. So it will have two solutions, so we just need to account for both the solutions. Okay, tan inverse of 20 divided by 75. Okay, so this will give you two solutions, so you have to use both the solutions to find the theta 1 and theta 2 from there. Okay, so you can see from Mohr circle, for this is the sigma 1 principal plane, first principal plane, and this is the second principal plane, also sometimes called major principal plane and minor principal plane. So you can see that this angle is acute, so the smaller angle from this equation, smaller angle will be corresponding to sigma 1. Okay, and you can see there that the obtuse angle will be, so what I'll represent it here with black color. So this will be theta 1. Okay, and this will be something like this. This will be theta 2. Okay, yeah, so whatever we got, you can add 180 to that and you will get the other one. Okay, so you know that property, 2 theta 1, or the difference between two angles is 180, twice of that is 180. Okay, so from there you can find the principal planes also, their orientation. Okay, so this we have done for the question number 1. So actually we have found some more parts. Okay, so I hope you understood that how to solve this, because this is very basic question, mostly asked in all competitive exams. It's very basic. Okay, especially with the angles. Okay, so that is there. So now moving to the other question. So we have solved first question. We have found the center of the Mohr circle, we have found the radius, and I will suggest you to plot that equation in some solver or in some plotting software, so that you will see that the exact things which you are getting from the equations you will see in the Mohr circle itself, because right now I'm not plotting it to the scale here. And then we found the principal stresses, and we found the maximum shear stress, and also we found the principal planes. Okay, that equation we saw. Now moving to the next question. So the next question is, so here what I have chosen a three-dimensional kind of representation of stress tensor. Okay, so the sigma matrix is 3x3 matrix, 3x3 matrix, so that you can find it for those cases, because those cases will be much more little bit involved. Okay, so that is there. So let's see this case. So in this question we have a stress tensor for a state of stress as given here. So you can see that all the components have same value of stress tensor 10. Okay, so now what it's asked, so as you have gone through, there is something called stress invariance. Actually it should be invariance here, not variance. It should be invariance here. I will correct it here. Stress invariance, not variance. Okay, so stress invariance. Why they are called stress invariance there is because you will see in a while when we will solve this problem. So they are a stress invariance, and they don't vary. Basically, they don't vary. I1, I2, I3 are called stress variant, and they don't vary with for a particular given state of stress, even if you change the representation of the stress tensor. So you can see in this problem, I told that these all are planes. So this one was y plane. This is y plane. Okay. So you can see then this is a principal plane. This principal plane. Further, if I draw another diameter, so you will find some another plane, and the values will be different. Further, I will draw another diameter, you will find another plane. Okay. Further, I will draw another diameter, you will find some other plane. So with this change of plane, always the components will be different. Okay. These components of tensor, stress tensor will come out to be different. These components, they will keep on changing as we will rotate the plane. But as you know, the circle is not going to change, the center of the circle is not going to change, the radius of the circle is not going to change. Hence, mathematically there should be also something which should satisfy it, or which should add to that. Means which should show that okay, if the components are going to change, but this at the end the stress tensor or state of the stress should not change. So these invariants are very important in that sense that even if I represent this stress tensor in some other form with some different values of these components, these will not change, these will remain same. Okay, these will not change. Okay, so that is the definition of stress invariance. Okay, and then how to use those stress variants to find the principal stresses. So there is a way we can use that stress invariance to find directly the principal stresses. We have already seen how to find the principal stresses in case of 2 dimension. So we have formula, mathematical formula to do that. So there is a way to find principal stress through stress invariance, and we'll see another long way also to do that. So I'll try to solve part 2 twice. Okay, so you understand in both case. Okay, and then we'll find maximum principal stress again. It is very important. So we'll see how that sigma 1, sigma 2, sigma 3. So what is the convention to follow, so that we always end up with a correct shear stress. Okay, so here it will be very important. We'll see that. Then we'll find something called a deviatoric stress tensor and hydrostatic stress tensor. So you might have seen in the lecture also, professor has told that what is deviatoric stress tensor and hydrostatic stress tensor, because there is we assume that in the linear elastic region the stress is linear basically. So we can decompose it in 2 components. One part of the stress tensor will be hydrostatic, and the other part will be deviatoric. So we'll find those components, and then we have to check whether this given state of stress, which is given here by this tensor, is it a uniaxial tension state, or is it if it is, how we can say that, and is it a pure shear state? If it is, how we can say that? And then we'll find the octahedral stress on normal octahedral stress and the octahedral shear stress. So there is something called octahedral plane, which you have seen in the lecture, that the octahedral plane. So how to define octahedral plane? So if you have your principal directions, so suppose this is sigma 1, this is sigma 2, and this is sigma 3. Okay, if you have sigma 1, sigma 2, sigma 3, or I would say not sigma 1, better way I'll say n1, n2. So this is n1, this is n2, and this is n3. So n1, n2, n3 are principal directions. Okay, remember these are not x, y, z, these are actually principal directions. So if these are or the direction of the principal planes, so if these are principal directions, so then a plane which passes in such a way, so there is a plane, I'll just representatively draw. Okay, So there is a plane whose normal, and this is that normal n, or not like that, n. Okay, so this n, if this n is n1 by root 3 and plus n2 by root 3 plus n3 by root 3. Okay, so it is kind of equally inclined from this n direction, or n vector will be equally inclined from the principal directions. That plane is called the octahedral plane. So this plane will be called octahedral plane. Okay, so we'll see that also, how to find what is the formula for finding the normal stress and shear stress on octahedral plane. Okay, so let's start this one. So the first we'll write the stress tensor. So solution 2. So our stress tensor is sigma. It is 10 everywhere. Okay, so the first quantity we have to find is, first is stress invariance. Okay, so how to find the stress invariance? So first one is sigma, I1, that is called first invariant, will be what? The sum of this diagonals. Okay, this, so we can just sum it up here, and that will give us the stress invariance. So it will be what, basically, if we write, even if we write in terms of, first I will write in terms of, for a general given this thing, given stress tensor. So sigma xx plus sigma yy plus sigma zz. Or if you want to write it in terms of principal stresses, so it will be sigma 1 plus sigma 2 plus sigma 3. Okay, so this representation is in terms of a general stress in tensor, and this is specifically if you have principal stresses. Okay, and as I told, it is a stress invariant, so it won't vary, it will remain same. Okay, for a given state of stress. So from here, if we see, so what will be the value of these 2, 3? It will be 10 for each, so it will be 30 MPa. Okay, so this is the first stress invariant, I1. Now coming to the second invariant, that is I2. So I2, how professor has told in the class, so you have to take each 2 by 2 matrix. So one is this, another one is this, and the other one is this, and you have to find what determinant of that matrix. Okay, to find the determinant of that. So I'll write first the matrices. So 10, 10, 10, 10 plus 10, 10, 10, 10 plus 10, 10, 10. So if you look this, if you find the determinant of this matrix, all the determinants will be 0. This will be 0, the other one will be 0. It means I2 is 0 for this case. Okay. And the third stress invariant is the I3, which is nothing but determinant of, actually, of this whole matrix which is given, basically. Okay, so it is nothing but the determinant of this matrix itself. So 10, 10, 10, 10, 10, 10, 10, 10, So by the property of matrix, you know that when all the elements of the matrix are same, then its determinant is 0. So I3 will be also 0. Okay. So we have found the stress invariant. So these three stress invariant I1, I2, I3, they will not vary with the representation of the stress tensor here. So if for some another plane this stress tensor gets changed, the components of the stress tensor gets changed, even then also the invariant I1, I2, I3 will remain same. Okay, they won't change. Okay. So now what is this next? So we have solved first part. What is the next part is? The next part says that we have to find all the three principal stresses. Okay. So for doing that, there are three ways. We will see. One is by using the stress invariant. So just we have found the stress invariant. So one way is using the stress invariants. So what happens is that basically we have to find the principal stresses. So for finding this, we have this equation sigma cube minus I1 sigma square plus I2 sigma minus I3 is equals to 0. Okay. So this is the equation. If we will solve this equation, the roots of this equation will be the principal stresses. Okay. So what I'll do, I'll mention here roots of above equation are the principal stresses. Okay. So if I just find the roots of this equation, we will get the principal stresses, and we already know I1, I2, I3. I've just found. Okay. So we know that I2 and I3 are 0, so it will be basically sigma cube minus 30 sigma square. I think I1 is 30. Just as 0 is equals to 0. So if you take sigma square common, it will be sigma minus 30 equals to 0. That means there are three roots. So sigma 1, traditionally what happens, you have to write in this fashion: sigma 1 greater than sigma 2 greater than sigma 3. So basically sigma 1 will be 30 and sigma 2 and sigma 3 will be 0. So now you can see that it has only one principal stress which is non-zero, rest of the two principal stresses are 0. That means if you have gone through the lecture properly, that means what is happening, you would have understood by now that I2 and I3 were 0, only I1 was non-zero. That means that this state of stress which is given here is actually a uniaxial state of stress, and we'll see. That is the part we will do later on. Okay, so because you can see that there is only one principal stress, there is no other principal stress, all are 0. Okay. So this is a way to find the principal stress. So we found sigma 1, sigma 2, sigma 3. Another way I'll solve is like, you can say how, from where this equation came, like how you wrote this equation, what is the genesis process, how it came. So we'll see that basically how we find the principal stresses. If you are not finding the principal stress invariant, so how you do that? In that case, what we do, we find determinant of this matrix, given matrix, like 10 minus p, or like I won't write p, I'll write sigma. 10 minus sigma 10 10 10 10 minus sigma 10 10 10 10 minus sigma. So basically I need to find the determinant of this matrix and put it 0. Determinant of this matrix you have to find and put it to 0, and then we'll find we'll find at the end the same equation. Okay, what I'll do it. Okay, so this is from here only, from this only we'll get this equation, basically this equation finally. Okay, So let's do it, because if you are not knowing already I1, I2, I3, so you can directly use this way to find. Okay, so what we will do, we'll just find the determinant. So it will be 10 minus sigma into 10 minus sigma whole square minus 100, then minus of 10 into 10 into 10 minus sigma minus 100, and plus 10 into 100 minus 10 into 10 minus sigma. Is equals to 0. Okay, so yeah, so let's open it. So 10 minus sigma, how this will be 100 plus sigma square minus 20 sigma, okay, minus 100. This is the first one, minus 10 into 100 minus 10 sigma minus 100, and plus 10 into 100 minus 100 plus 10 sigma is equals to 0. So you can see that this cancelled out with this, and this cancels out with this, and this cancels out with this. So what we are remained with, 10 minus sigma, this will be sigma square minus 20 sigma, and minus this will be what? So you can see that this minus, and there is another minus inside, so this becomes plus. So plus, and 10 into 10 is 100 sigma, okay, and then plus, and this is plus and this is plus, so it will remain plus, so it becomes 100 sigma is equals to 0. Now you open this, so it will be 10 sigma square and minus 200 sigma, then minus sigma cube, and plus 20 sigma square plus 200 sigma to 0. So this 200 gets cancels out with this, and we are remaining with 30 sigma square minus sigma cube is equals to 0. So the same equation which we have written here, you can see. So just I need to multiply with the minus sign both sides, so it will be same equation. So basically if you take sigma square outside, it will be 30 minus sigma is to 0. Okay, this is also called characteristic equation. So basically this is called characteristic equation also, characteristic equation, you can look it up also. Okay, so the same equation we got, and from this the solution of this equation will be the answer. So it basically it will be a cubic equation. There will be 3 roots, okay, because it's a 3 dimension. Okay, means we are having 3 different we are representing our stress tensor in a 3x3 matrix. So 3 roots again, that sigma 1 will be 30 MPa, and sigma 2 and sigma 3 will be 0. Okay, so we found from both ways. One is the way in which you already know the principal, you know the stress variant, so you can directly plug in the stress invariant in this equation, very important equation. You can plug in with their sign. Okay, these signs are fixed, you can't touch these signs. Okay, this minus, this plus and this minus are fixed. Okay, you can't touch it. You have to put the value of I1, I2, I3 with its sign, with the whatever sign comes, you have to put with that sign, and subsequently you will find the value. Okay, so we found the principal stresses using both the methods. Now coming to the next part. Why I showed, because it's very important. Sometimes you don't stress invariants are not asked, so how to solve it, or sometimes it is easier to get the solution using the other equation. Okay, so we found the principal stresses using two methods. Now coming to the third is the maximum shear stress. Okay, so the maximum shear stress is maximum shear stress. So what will be there if the principal stresses are arranged as that sigma 1 is greater than sigma 2 is greater than sigma 3. So if the principal stresses are arranged in this fashion, so we have to first make sure that your principal stresses are arranged in this way. Then we write the maximum tau max, maximum shear stress as sigma 1 minus sigma 3 by 2. Okay, and you know that, so this is for 3D case, okay, where you have a 3D case. Okay, if you don't have that, it means in a general stress tensor. Okay, I would not write 3D, I will write general 3x3 stress tensor is given. So in that case you will have three roots obviously. Now for plane stress case with 2x2 stress tensor is given. So if the stress tensor is given for a plane stress case, which is a 2x2 stress tensor, so in that case you have to arrange sigma 1 is greater than sigma 2, and then the tau max will be sigma 1 minus sigma 2 by 2. Okay, basically from here what we see that the maximum shear stress is half of the maximum value of the principal stress and the minimum value. Always the maximum value and the minimum difference between the maximum and minimum value of the principal stress, half of that. Okay, so here this is the maximum principal stress, this is the minimum principal stress, and here this is the maximum principal stress and this is the minimum principal stress. Okay, this is the maximum here and this is the minimum principal stress, and here this is the maximum principal stress and this is the minimum. So it will be always half of the difference between the maximum and the minimum principal stress. Okay, so for our case we know that sigma 2 and sigma 3 are 0. So for our case the tau max becomes 30 minus 0 divided by 2, that is 15. So the maximum shear stress becomes 15 MPa. Okay, yeah. Anyone having any doubt till now? Any doubt? Okay, good. Okay, Arjun has a doubt. Yeah, is there a doubt? Oh, okay, fine. Okay, sure, thank you. So this is very common question, and generally this is asked in a sense that like what will happen, that one component will be negative, sigma 2 and sigma 1 will be positive. So just what we do, we subtract the sigma 1 and sigma 2. We have to check properly for sigma 3. Okay, so let's I'll just give an example here. So let's say sigma 1 is 30 MPa, sigma 2 is 10 MPa, and sigma 3 is minus 15 MPa. So in this case, if I need to find the tau max, so it will be what? So I have arranged in this fashion only. So it will be what? 30 minus 15 with the sign. Okay, we have to put with sign by 2. That is 45 by 2. That is 22.5 MP. So what people do that they just consider this two value. Sometimes they don't bother it, because if you have to solve this equation as I told, so you have to look very carefully at all the three this thing solutions, or the three roots of this equation. You can't just have look at two and you can say it is fine. And the most embarrassing situation comes, so this is one example I gave. The other is one I will give also. Let's say sigma 1 is 20 MPa, sigma 2 is 5 MPa, and sigma 3 is 0. This is the most bad situation. In this, they will just don't consider this 0. So that is causes problem, and the result will be wrong. So the tau max will be 20 minus 0 divided by 2, not 20 minus 5 divided by 2. Okay, so it will be 10 MP. So what I have learnt, and what also professor has said in the lecture, and what I have personally liked is like that always make the habit to represent the sigma 1, sigma 2 and sigma 3 in a fashion that always sigma 1 is greater than sigma 2 is greater than sigma 3. In that case you will never have any issue. Just subtract sigma 1 from sigma 3 and divide by 2. Your answer will be always true, always correct. Okay, so that is an important point here. Okay, now come to the next one, that is I think the fourth part. Fourth is deviatoric stress and hydrostatic stress tensor. Okay, so now yeah, so why we are not using here is because we have a three-dimensional state of stress, no? So that formula is valid till we have sigma xx and sigma yy and tau xy. You can see that in this formula so basically this is also represents the maximum shear, because that it becomes the radius. So square root of this is also maximum shear. So you can see that we have only sigma xx, sigma yy and tau xy. So we can use this formula when we have a plane state of stress. That means the matrix is represented by 2 cross 2, not 3 cross 3. If we have 3 cross 3, we can't do that. Okay. So in our case, which we are solving right now, we have a 3 cross 3 matrix. So that is why we are not able to use. It's just like a this one basically is a subclass. Basically, you can get it from the other one. Means if we use a 3 cross 3, you will get that equation. From this, you will get that equation. So it is a special case, because it's a plane stress case. So it's a special case. But this case is a general case, a generic case. So in generic case, you should know what is the values of all the stress, principal stresses, and from there you can get the value of the shear stress. Okay. Yeah. 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 So previous one was a plane stress case, so we used those equations. Okay, but this is a generic case. A general, the stress tensor is represented as a general 3 by 3 matrix. So here we can't use, because we have other components also. Okay, so because of that we have to go with the case we are using this principal stresses to find tau max. And even there, so even you have seen in the lecture also, if you plot the Mohr circle also, so from there you can also understand why it is the difference between the maximum and the minimum, because the biggest so if I hope you all have gone through the lecture videos. That is my request to you, because you will be having much better understanding in that. So if you remember in the lecture, when professor drew the Mohr circle, when he had 3 principal stresses, so there were 3 circles he drew. There was 2 small circles which were inside a bigger circle. So the tau max will always be calculated from that bigger circle, not from the small circle. It will be calculated from the bigger circle, and the bigger circle will be drawn only when the points are most far apart. Okay, so those points on the x-axis, on the horizontal axis of the bigger circles, are sigma 1 and sigma 3 actually. Okay, and sigma 2 lies in between. Okay, so that's, I'll draw it here. If I'll draw, you will remember, you will understand what I'm trying to say. So from the point of Mohr circle, suppose sigma 3 is this one, sigma 2 is this one, I'll write 3 here, I'll write 2 here, and sigma 1 is this one. Okay, so as I told, the value should be in that order. Okay, and you can see it is in that order. Okay, now we'll draw the Mohr circle. So what we draw, that we draw a circle between these 2 points like this, something like this. Okay, this was one. Then what we do, we draw another circle between these 2 and 3, something like this. And then what we do, we draw another circle which encompasses these 2. I'll change it little bit. So actually it should touch these 2. Okay, I hope you understand what I'm trying to say here. It should touch those 2 circles. Wait. Okay, so the Tom X is always represented. So we have to find what? We have to find the center of this circle. Center of this circle. Okay, and from the center of that circle, you have to find the radius of that, basically. Radius of that circle. And the radius of that circle, so I will say the radius of this circle represents the maximum shear. Okay, so this circle radius represents maximum shear. Okay, so that is important. So that's why we have sigma 1 minus sigma 3. Okay, now coming to the next question, which is I think decomposition of the stress tensor into deviatoric and hydrostatic parts. Okay, let's do that. Okay, so this is fourth part. So as I told, the stress tensor, which is sigma, can be decomposed in 2 parts, because we say that we are in a linear regime, so we can do it. Okay, so we can combine 2 stress tensors to make it the final stress tensor. So it will have one we called as sigma hydrostatic. Okay, and another one is called sigma deviatoric, and it is a special one, deviatoric. So we'll see what is the special one, speciality of deviatoric. Now first let's find the tensor. So the sigma, I'll write the here hydrostatic like sigma hydro, or it also sometimes called as isotropic. Okay, so hydrostatic is nothing but 1 by 2 of sigma 1 plus sigma 2 plus sigma 3, 1 by 3 of sigma 1 plus sigma 2 plus sigma 3. Okay, this is the magnitude, means this is the value which should be because it is a tensor, so it will be a stress tensor, it will be a in a form of matrix, so it is something like this: 1 0 0 0 1 0 and 0 0 1. So basically this is the value just, and this is the matrix associated. So this is a constant value and this is a matrix. So if I put the value of sigma 1, sigma 2, sigma 3, it will be 1 by 3 into 30, if you remember, and it will be 1 0 0 0 1 0 0 0 1. So basically it will come out to be 10 0 0 0 10 0 0 0 10 MPa. So this is hydrostatic. So what is specific about it, this one, is that you can see that it has I2 and it's acting in the three planes. The stress, you can see that acting on three planes: sigma 1, sigma 2 and sigma 3. Okay, so it only either extends or it only compresses this component. Okay, it either extends, cause extension, or cause compression. Okay, so the example of this kind will be, the very good example will be, suppose we in civil engineering or in mechanical, we suppose there is a cube of the concrete or some brick. Okay, so we have some brick, suppose let's say there is some brick kind of thing, or some cuboid kind of thing, sorry. Okay, so I draw like this. Something like this. Now if I have kept, if I suppose keep it underwater, okay, so suppose this is at a height of some 200 meters below water. So suppose this is below water in 200 meters, this is what. Okay, so now this cube, or you can say a cuboid, something brick kind of thing, I suppose I am saying it is a brick. Okay, so now it will be subjected to the water pressure. Okay, and which will be actually we know that the water pressure applies normal to the surface and it acts towards it. It will be a compressive force, something like this: compressive force in this direction, compressive force in this direction, and compressive force in this. So this is called hydrostatic. Okay, so it will be pure in this fashion only. Every plane will cause a compression in it. The water pressure will cause a compression. Okay, so this is an example of this. So this is the hydrostatic part. Now how to find the deviatoric? So as I told that the sum of hydrostatic and deviatoric is the total stress tensor. So we have already defined what is hydrostatic. Okay, so we can find the deviatoric, okay, from this equation itself. So let's find that. So the sigma deviatoric tensor will be what? 10 10 10 10 10 10 10 10 10 minus 10 0 0 0 10 0 0 0 10. Okay, so if you see finally what will be the answer, if you subtract these two, it will be 0 10 10 10 0 10 10 10 0. Now if you see properly, in this case what you are seeing, that only non-diagonal terms are there, they are non-zero. All the diagonal terms are 0. Okay, and you might be remembering that when the diagonal terms or some sigma 1 plus sigma 2 plus sigma 3 is 0 for this, then it is what? It is actually a pure shear case. That means this sigma deviatoric is actually a pure shear stress. Deviatoric stress is actually a pure shear stress. Okay, and this is a very important property of deviatoric stress. So basically it causes deformation, shape change. This component causes shape change in the shape. Okay, it deforms out, like it will act in a sense that it will change the shape of the object, of the body which is subjected to this stress. So basically if you see, the hydrostatic stress causes change in the size. You can see that. So if in the case of water, the brick will be compressed, so its size will it will try to shrink, reduce in the size. But in deviatoric, it will try to change the shape, because it will be actually a pure shear, and you know in shear the shape changes. So that will happen in deviatoric. Okay, so this is also pure shear stress state. Okay, so we have found the hydrostatic stress tensor also, and we have found the deviatoric also, and we say that the total stress tensor is a linear combination, or it's just a simple combination of hydrostatic and deviatoric. When we are saying that we are in the linear elastic thing, everything is linear, so then we can do that. And this is widely used also in plasticity, when you will learn about plasticity in further courses, then you will understand. Yeah, Arjun has a question, I think. Yeah. Okay. 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 Hmm. Hmm. Okay, so like, yeah, so basically deviatoric is always in a sense that deviatoric is a concept which is here, enshrined here. Okay, so basically we, most of the time when we learn about it, we learn in a sense that when we are decomposing the stress tensor. Okay, when we are decomposing, where when you say that the I1 is 0, then you are saying that it is an actually pure shear, because that's why I wrote here pure shear, because pure shear is much more general than deviatoric. Yeah, so it is important to express it as pure shear, because deviatoric is a concept which is there because we are trying to decompose it in two parts. There will be like in this course we can't discuss that because it is out of the scope of the course, but there is a reason for that, why that will be mostly dealt in plasticity. So what have scientists have done, they have decomposed it into two parts to study further the behavior of the material, okay, which is subjected to some state of stress. But if suppose you find a stress, so if I give an example, so let's say example is sigma is given, and it is given like minus 10, 5, and here 8, I believe 5, 8, and this is 20, and this is also minus 10, and this is 7. So now you can see that if you sum the sigma xx, so if I'll find I1, what is that? Nothing but sigma xx, the sigma yy, the sigma zz. Okay, so you can find that it is coming to be 0. Okay, so actually this is a pure shear case. Okay, it is a pure shear. Here only shear will act, nothing else. No axial, no normal will act on any plane. Only shear stress will act. Okay, so you will have tau xy, tau yz, those components will be there, but no sigma xx, sigma y component basically. Okay, so this is a kind of condition for pure shear. Yeah. 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 I think I lost. I can't hear. Hello. Hello. I think I can't hear. Hello. I think I lost the internet. Okay, it's trying to establish. Yeah, am I audible? Yeah, actually there was a connection issue. Yeah. Yeah, go ahead, Arjun. I couldn't hear your question fully. Yeah. Yes, yes. 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 Yeah. Yes. 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 Yeah, it's just two way or different way of presentation. Correct. Yeah, because this see, if you remember, if you see, so basically sigma 1, sigma 2, sigma 3 is what is actually a I basically, no, I1, because this will not change. You, if you see this sigma 1, sigma 2, sigma 3, this will not change. That means the hydrostatic depends on I1. Okay, and what is I1? That I1 is an invariant. It will never vary with the state of, if the representation of the state of stress, a stress tensor changes. If the representation of the stress tensor changes, okay, the stress tensor remains same, just its representation, its components get changed. I will come to the end of this when I'll talk about next two questions. We'll see that. So because sigma hydrostatic remain depends on stress invariant, whatever representation, whether I write in the way I have written right now 10 10 10, or if I write in terms of sigma 1, sigma 2, sigma 3, whatever way I write, it will remain same, because it only depends on this. Hello, yeah. Is it fine? Yeah. Now coming to the, yeah, coming to the deviatoric part. Now as you know, this is remaining constant, but what happens, deviatoric depends on hydrostatic, which is invariant, and sigma, but this sigma is not invariant. It will vary. This representation will vary from different way to different way. So the deviatoric may be different, because if this I will put as a representation of only in the sense of like where only the principal stresses are there, then it will become the deviatoric will become different. Okay, but if I represent it in a different way, the deviatoric will be different. Okay, because but the hydrostatic will remain always same. The point is, this will always remain same. This is depending on the way how we are representing the sigma. I hope that was fine. Okay, I think Priyanka was also asking question. Okay, 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 okay. Thank you. Okay, okay, good. Okay. So as you can see, the hydrostatic depends on the stress invariant, and you know stress invariant does not change with the representation of the stress tensor. What are the components? Because as you will move along the Mohr circle, you will have different planes, and different planes will have different representation of the stress tensor, but this will always remain same, so that we conclude from that the sigma hydrostatic will remain same, it won't change because it depends on that. But the because we can write the deviatoric stress for any, because for any given representation of the sigma stress tensor, we can decompose it into two parts, so this could change. Okay, and if we will at all write in this, so we'll get only the other components, means we'll get the components in a sense that they will represent the same state, but it will always represent a pure shear. That is no doubt, that will always represent a pure shear case. Okay, now coming to the next part, that is yeah. So now the next part is the given state of stress is uniaxial tension justify? So that's what we will see. So you can see that there are many examples from, or many at many places we can see that. Why? First one, that I1 is non-zero, I2, I3 is 0. So as you remember in the lecture also, professor said that when I2 is 0, suppose I2 is 0, so obviously I3 will be 0. Okay, most of the cases it will be 0. So I2, I3 remains 0, and only I1 is non-zero. That means it is a uniaxial state of stress. That is one way, or one of the like one way we will say that. Another way we can say that only sigma 1 exists, sigma 2, sigma 3 are 0. That means again it is a uniaxial state of stress. Okay, and we found the sigma 1, sigma 2, sigma 3 by two different methods. Okay, so that is another way to see that. Okay, so there are two ways we can see that. So I'll go about here, like fifth part. So we have I1 as 30 MPa, and sigma I2 and I3 are 0. So this is already a condition of uniaxial state of stress. Uniaxial state of stress. Okay, this is already a condition of uniaxial state of stress, that I1, I2, I3. I1 is non-zero and I2, I3 is 0. Another view was that we had principal stress values. So 30 MPa was sigma 1, and sigma 2 and sigma 3 were 0. So that is another way we can say it is a uniaxial state of stress. Now you can see that in general. So what I can do, I can represent it in the sense like sigma 1 0 0 0, sigma 2 0 0 0, sigma 3. Same stress state I can represent, I'll call it as sigma star. Okay, a different representation just. So it will be what? 30 0 0 0 0 0 0 0 0. So the same state where we had all populated 10 10 10 everywhere. Now it is just like this. It's just nothing but it is a uniaxial state. And why? How it happened? Because we saw, because of the Mohr circle. Because if we go to a different plane, it will be a different representation, but the state of stress will remain same. So here you can also see I1 plus I2 plus I3 will be 30, I2 will be 0, and I3 will be 0. Okay, so this. Next was is the given state of stress is pure shear justified? So we have justified for the fifth part that why it is uniaxial tension. Is the given state of stress is pure shear? So we saw that what are their conditions for pure shear? What are the conditions for pure shear? So the conditions for pure shear is, for the state of pure shear stress. So what is the condition is that the I1, that is sigma xx plus sigma yy plus sigma zz in any general state of stress, or sigma 1 plus sigma 2 plus sigma 3 when you have principal stress. So this should be 0. I1 is equals to 0 is a condition of pure shear. You have professor have already spoken about this in the class. Okay, so we see that in our case I1 is non-zero, it is not 0. So obviously this is not a pure shear stress state. So it is not a pure shear stress state. Okay, so if you, these are the very few quick checks. So if suppose you find a problem, suppose something like this, you find a problem minus 20, 50, 50 and minus 20. So you can directly say that, oh, it's a pure shear state of stress. You see that the I1 is 0. Okay, just it is been represented. Okay, so from there, if you will find the, if you find for this case, if you find the sigma 1 and sigma 2, suppose you have find the sigma 1 and sigma 2. So because you know in 2D sigma 1 and sigma 2 will be same, because it's a pure shear state of stress, they will be actually same, but just of opposite signs. We have drawn the Mohr circle for the pure shear state of stress last time, so they will just be of opposite signs. Okay, but their magnitude will be same, just one will be positive and another will be negative. Okay, so that you have to just look through. Okay, so this is the yeah. Oh, sorry. Yeah, correct, thanks. It should give a 0, no? So it should be obviously plus here. Okay, so in this case like this is one of the check, and the check for uniaxial stress I told you how to check it using I2 and I3. So just check whether I2 and I3 are 0 and I1 is should not be 0. So that is for uniaxial. Now moving to the next one, which is so octahedral normal stress. So I'll talk about little bit more about octahedral plane first. Okay, so that you guys also get a feeling about it. So let's first talk about octahedral plane. Octahedral plane. Okay, so as you have seen in the lecture also, so if you have if the directions are not the normal I, j, k or x, y, z, if they are the actually the directions of the principal planes. Okay, principal planes. So I'll represent suppose this as n1, and these are vectors. Okay, remember that these are vectors in themselves. Okay, n1, this is n2, I'll draw an arrow, n1, n2, and this is n3. Okay, so you know that they will be mutually perpendicular, that you have known by now that the principal plane will be mutually perpendicular. Okay, so if we represent the directions as the principal directions, so the normal to principal planes are the principal direction. Okay, so n1 vector, n2 vector and n3 vectors are principal direction. Then if I imagine about a plane, okay, about a plane which is something which is equally inclined from these three directions. Okay, a plane which is equally inclined. So this is actually the definition of octahedral plane. A plane equally inclined from all the three mutually perpendicular principal planes or principal directions basically is known as octahedral plane. Okay, so if you see this plane here represented by this red color, so this normal to this plane will be the n octahedral, we call it n octahedral. Okay, and in terms of n1, n2, n3, it will be 1 by root 3 n1 plus 1 by root 3 n2 plus 1 by root 3 n3. Okay, so that's how we get the octahedral plane. So we have done in our first and second doubt session about how to find the stress from stress tensor, how to find the stress vector, and then from this stress vector how to find the normal stress and shear stress. Using same concept we can find this octahedral normal stress and octahedral shear stress, but right now we will do it by the formulae, basic formulae. Okay, so if we know if sigma 1, sigma 2 and sigma 3 are the principal stresses, so from that expression only it has been reduced in this form, like when we have sigma 1, sigma 2, sigma 3 as the principal stresses. So the sigma octahedral, that is the normal octahedral normal stress, it is octahedral normal stress. So this sigma octahedral will be 1 by 3 sigma 1 plus sigma 2 plus sigma 3. Okay, 1 by 3 sigma 1 plus sigma 2 plus sigma 3. So our case it will be what? 1 by 3 30, that is 10 MPa for our case. Okay, so remember that here it is in terms of sigma 1, sigma 2, sigma 3. There is also a representation. I would suggest you, if you are following some book, you go through that book, you will find a representation of sigma octahedral in terms of sigma xx, sigma yy, sigma zz, tau xy, tau yz, tau zyx. You will find a representation also. There is a representation for same. Okay, so that is sigma octahedral. So our case we will find it 10 MPa, and the next is the tau octahedral. So I hope you understand that in this plane there will be a, what is the meaning of it all? No, so in this plane there will be a stress tensor, a stress vector, which will be Tn octahedral or T octahedral, like here. So that will be what? That will be decomposed into two components. One component will be this, which will be along the normal. Another component which will be on the plane. So the plane component will be shear, and this component will be the normal. Okay, so these two components only we are finding. So here we'll find tau octahedral, that is octahedral shear stress. So tau octahedral formula is 1 by 3 sigma 1 minus sigma 2 in terms of principal stress whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square root of this, and 1 by 3 divided. Okay, so this is tau octahedral. Okay, so we know what is the value of sigma 1, sigma 2, sigma 3. So tau octahedral is 1 by 3, and here sigma 1 is 30, sigma 2 and sigma 3 are 0. So 30 square plus this will be 0 square plus this will be 30 square. Minus 1 minus this minus square is plus only, the square root of that. So it will be 1 by 3, so it will be 2 into 30 square and square root of that. So if I take square root here, so it will be root 2 by 3 into 30, so that will be 10 into root 2, it will be 14.142 MPa. Okay, so the tau octahedral or octahedral shear stress will be 14.12 MPa. Okay, so that's how we will find the octahedral shear stress. And again there is a representation you will find for the tau octahedral in terms of sigma xx, sigma yy, sigma zz, any given this thing, given state of stress. There is that is available. It's a big long expression. In terms of sigma xx, sigma 1, sigma 2, sigma 3, it reduces to a simple expression. Okay, so I hope we have finished all the parts. Okay, so if anyone has having any doubt, please you can ask. Yeah, Priyanka. Yeah. Ah. Okay. Ah. Okay. Hmm. Okay. Yes. No. Okay. So see, you are going to study that in further lectures. I hope in maybe in the 5th or 6th week. What happens? We'll see. Okay. Let's see. Little bit. I'll tell you. I don't want to spoil everything now. Okay. So your question is how shear is coming. Basically, if I understand it correctly, the question is how the shear is coming in place when sir is applying a torque or a okay. So let's say this is a chalk piece. I'll draw. Okay, and this is suppose the axis of the chalk. So if we have to give a anti-clockwise, so I think we should make a symbol like this, and we can make like this. Okay, basically either you rotate in an anti-clockwise or clockwise fashion, only the angle will differ, but it will fail by shear basically. Okay, now what happens actually when a body is subjected to a torque? Basically what is happening, if I show you some loading, so it is like this, it is the load is applied like this, it is a torque. Okay, it is applied in a sense as a torque. Okay, so what this torque causes, actually if you see, so this was the original section, suppose, of the chalk cross section I am drawing. Okay, so what it caused, that after the chalk is rotated because of the torque, it will do what? If I look at very small portion, suppose I am interested only in this portion, so basically what will happen, this portion will rotate by some angle theta. When we are applying a torque, if I'm very small portion I am drawing here, this very small portion, this red color region, so what will happen, it will rotate. When we will apply a torque, it will rotate, and that rotation will be actually causing a stress something like this, which will be tangential basically, and it will depend on how far is that place where we are finding the stress. if I say this is the radius of the circle r, so it will depend, that value of tau will depend, this is suppose called tau here, okay. So that tau will depend on r, it will be some function of r, how far it is. And if you see, if I go, if suppose if r is 0, that is if I am at the center, the tau will become 0, that shear will become 0. So what happens when we apply torsion, the torsion causes the shear deformation in the cross section, it causes shear in the cross section, and due to that only the state of stress when professor is rotating the chalk either clockwise and anti-clockwise, it causes shear in the cross section, and due to that shear only, now what happens, because there will be no normal stress in this case, only shear, and shear means pure shear, okay. So when it will be pure, it will be a pure shear because there will be no normal stress there. So in pure shear state of stress, you know what will become states of stress, suppose 0, tau, 0, something like this, okay. So that means now you need to find how, now the question is how the chalk got failed in a different angle, because in that case, in case of pure shear or in the torsion case, the chalk fails somewhat like this at 45. It fails either in this plane, in the type of rotation, if that varies, if the type of rotation varies, so either in this or in this way. So it will be actually from this axis 135. It depends whether you are rotating it clockwise or in another sense, anti-clockwise. Okay. Okay. So that means we first came to know that there is, you are going to learn this concept that is called pure torsion. This is a concept like pure bending. You will also learn here pure torsion, and in torsion there is a theory behind it, like there is a theory of pure bending or theory of bending, there is a theory of torsion also. So in that theory what happens, like if you apply torque, only torque if you apply on a body, it generates stress which is shear in nature, and it applies on the cross section. So basically it shears the cross section, and it is such that value of that shear is a function of radius. If the radius is bigger, the shear stress will be more. If the radius is very small, the shear stress will be small. Okay. Now coming to the, so from this we learned that the state of stress will be shear stress. Okay, this is the concept, this is the theory which we are going to learn. Now once if we know that the state of shear, state of stress is shear, now let's draw the Mohr circle to understand it. So I will draw the Mohr circle. So you remember we have drawn the Mohr circle for shear stress last time, and we have seen that that the Mohr circle is centered about origin first of all, okay. It is centered about origin, and this is plane 1, this is plane 2, okay, and the maximum tau max occurs here, the maximum shear stress occurs here, and the this is what, this is x plane and this is y plane. If you might have remember this, I did it in the last class. This was the x plane, and even in the lecture this is the y plane, okay. Now we know that chalk is a brittle material. Chalk is a brittle material, okay. It is a brittle material. So mostly brittle material fails in tension, fails by tension. They will mostly fail by tension, they won't fail by shear. The the other example you might have seen in the lecture is the cup and cone failure. The cup and cone failure is something like, if you have a MS steel bar, reinforced bar, so it will something like a cup here, and it will cause a cone shape here, something like this, something like this. This is cup and cone failure which happens in steel basically. In chalk is a brittle material, so it will mostly fail by tension, okay. Now question comes, where is the maximum, where is the principal plane? So you can see the principal plane is at what angle? It is actually at 90 degrees from the x plane, it is at the angle either 90 degree. So I will represent it. So one is theta 1, which is at 90, and another one is theta 2, which is at 270. Correct? So what will happen? As I told you last time, this theta 1 here in the Mohr circle, half of it we will use in the actual problem. So what is the half of 90? Because it is, this angle becomes 2 theta. You have just seen the equations of Mohr circle. The equation of Mohr circle is in when we draw, it comes as 2 theta. So we have to half it. So half means 45. That means this sigma 1 will exist at 45, where only the normal stress will, this is the principal plane, sigma 1, and only normal stress will be there, and there will be no shear stress. So because of that torsion, because of that applied torsion either in the clockwise or in the anti-clockwise, either on the 45 degree angle or on the 135, which is half of 270, there will be a principal stress and there will be no shear. And because of that, and the material being a brittle material, it will only fail in that principal plane where the principal stress is acting, and that is why it fails at 45 degree when we apply a torque on a chalk piece, because it is a brittle material. Brittle material fails in tension only, and because of that property, the tension comes at this 45 angle. When we do it another way, the means this point translated to this and the other point gets translated to that, because of the either it is a clockwise sense of torsion or it is an anti-clockwise sense of torsion. That's all. But it always fails at 45. So that is the reason why it fails 45, because the 45 degree angle shows the plane which is a principal plane. Understood? Yeah. Okay. And you will study that why that torque causes shear, because there is something called pure torsion theory, pure torsion. So that will be covered mostly in this course. So we'll see that from that you will understand, okay, when some object is applied with pure torsion, so it gets into pure shear case, only shear acts, and that's why we know that the Mohr circle will be like this. Okay. Okay. Ah. Yeah. 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 Okay. So see. Actually, okay, I understand your point. See, suppose this is one circle. Okay, something like this. So suppose this is a thin walled pressure vessel. Okay, don't go with the thickness, and it is just for the showing, for the purpose of illustration. Okay, it is not actually that much thick, it is thin only. So what professor did, that is because of symmetry, because suppose you are applying pressure inside, no, so pressure will be normal like this, it will be normal like this. So because it's symmetric, you can just study the half of the this thing of the problem, no need to go for the full scale problem. So what he did, he divided into two parts, and it should be semicircle, no, it is giving me parabola like this. He did, okay, something like this. So assume that this is a semicircle. So what he said, that because of that this internal pressure, there is a pressure inside it. Okay, so pressure is acting. something like this. The pressure is acting. So what will happen? This pressure will have what? It will give you a reaction, something like this at the ends if you cut. Okay, so the resultant of all this pressure will be giving you something like this, some resultant of force in the vertical direction. Okay, but you can see that these arrows which I am drawing, actually they are perpendicular to the surface. Wherever I draw, suppose here I draw, so I will draw a tangent and it should be perpendicular. If I draw here, I should draw a tangent, it should be perpendicular here. So there are some components of pressure which will contribute to this direction also. In the x, if I say this as x, suppose this is y and this is x. But you see that if it is causing a horizontal reaction here h, so it will cause a similar reaction here h. And basically what will happen, I have to draw the reaction. So you can see the pressure is causing it to move outward. I am drawing this not as a reaction here, I will delete this part. This is, I am saying, the pressure horizontal component. Okay, and this is the pressure vertical component. Actually it is trying to pull it up and open it apart. What will happen, suppose if this balloon is there, so if we blow the balloon, but it try to expand it, no, the air we blow, it try to expand the surface of the balloon. So something similar, it will try to open it in a sense. Here it will try to open it, this thing, and it will try to push it up, this vertical force. So how the reaction will come into play? The reaction will try to do the opposite thing, which will be from this piece of metal. This metal piece will apply the reaction. No, so it will try to what? It will try to keep it in its place. It will cause no. Why you are going outside? Be there. It will give you a resistance, which is called an internal resistance. So the pressure, the material will apply a reaction in the sense like this, and a pressure in the sense, a reaction in the sense like this. Okay, so I will draw those with another color. So the material will apply a pressure, a reaction, a force in this manner and a force in this manner to overcome the force of the pressure. So now you tell me, these two components will be what? They are actually applied in the same direction and same magnitude and to each other. So we can say that these don't play a role. Means same magnitude and are in the same direction. This is force, not stress here. I am talking about force. So that's why he said that okay, we don't need to consider this, we need to consider this, because this will cause the stress in this material which is here, this material, and that's how we find the stress in the material using this force. You understood? Because we are finding that the reaction is coming equal and opposite. I think you didn't get it. Means yeah. Yeah, so because these two forces won't cause it to, these two forces are not respect to cause any stress in this material, because they are not aligned with the material. No, see, when we are talking about this vertical force, this force P vertical, and I'll say something else to this blue arrows, which is actually the reaction from the material, this will play the role, no, in the resistance of that vertical force which is exerted by the internal pressure, which is represented by black arrow PV, this PV in the material. Because like if I draw the next half, this force will be in the other direction. This arrow I will draw in the other direction. It will be something like this. It will be something like this. No, like this is actually a distributed thing. I am drawing a resultant of it. Maybe next time I'll come up with a better explanation to this. Okay. Yeah, Madhav has commented that balancing forces along x-axis from 0 to pi vanishes horizontal component. Exactly what he said. So you will, when you will do that balancing, it will be 0 basically. Yeah. Hmm. Okay. Okay. So what I'll do, I'll try to uh, connect with the other TAs and I'll let them know. Okay, if they are not answered, or if it will be related to my this lecture. I have answered. Somebody has asked question about my lecture, so I have answered that question. But I'll see with the others. Okay. Okay. Regarding assignments, I'll I'll uh, I'll check with the other TAs and I'll let you know. Okay. Uh, yeah. 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 Okay. So yeah, I hope you have understood uh, today's topic and today's discussion. If there will be any questions, you please put in forum. Just mention that about the session, this problem solving session. Just mention that. I'll reply to that. Okay. Yeah. Thank you, Madhav. Thank you, Lokesh. Yeah. Thank you. Thank you, Arjun. Okay. Thank you all for joining, and we'll meet next. Yeah. Thank you. Thank you, Brinker. We'll meet next week. Okay. Yeah. Thank you, Francis. Okay. Bye bye.